Hello, and welcome to our Force.com webinar, Multi-Tenant Magic, under the covers of the Force.com data architecture. As you may know, Salesforce.com is a publicly traded company, and therefore we do need to share this safe harbor statement with you to let you know that any forward-looking statements are just that, forward-looking statements. If you have any more questions about this, you can find it under our website under the Investor Relations section. With that, I would like to introduce Craig Weisen.
Good morning, everyone. Today's talk is going to be a little different than most of our talks, which are more about Salesforce functionality. Today we're going to be talking about how Salesforce and Force.com in particular work. The interesting secret is that in addition to our apps, which we're very proud of, is that Salesforce has been building a general purpose computing platform, or platform as a service, which is what we'll be telling you about today. Now, the reason that we're more interested recently, and you'll be hearing more of this from us, is not only that we're proud of many of the things that we've built, but we're now asking IT departments, our customers, but also third-party developers to build things on top of Force.com. So we want to explain how things work under the cover, which brings us to our agenda today. Multi-tenancy is really a good proxy for what differentiates Salesforce's implementation of platform as a service, particularly a data-focused platform for building data-focused applications. So we're going to start off talking about a few slides about what we like to call our religion about sort of true multi-tenancy, which is what the next few slides will be about. And you'll see it's a fair bit different than what other platforms and other providers do. Now, a lot of what we're going to talk about today is very focused on a database, and Salesforce is sort of an expert at building or providing a virtual database for each of our tenants, and we do this on top of a much smaller number of physical databases. So the bulk of the slides will be talking about interesting things about our schema design, our metadata, our schema for customers, as well as query optimization, things of that sort. And then hopefully, time permitting, we'll talk about how we use those concepts in building applications. So we'll jump into the religion discussion, and we'll start off with this messy-looking slide, which shows sort of the pre-platform view of the world of enterprise software, which most of you are very familiar with. We have, in this case, lots of different tenants who have their own hardware stacks and lots of different operators who are operating and running different databases and application servers, which are possibly different vendors. And this is meant to show that there's a lot of waste here. There are a lot of computers. If we take the example of Salesforce with 50,000 plus different customers, there are upwards of hundreds of thousands of computers that Salesforce has been able to replace with a much smaller number. But there are other inefficiencies here. In addition to the so-called platform support matrix of death, where software vendors have to support multiple database servers and multiple application servers, there's another very important thing here, which is the different customers may not be on the same version of your software. They may not be on the same schema. So in terms of innovation, the software vendor has to patch and otherwise support and maintain lots of different versions. And so we're all familiar with these inefficiencies. So moving along to this much simpler picture, which is sort of the Salesforce view of the world, and is sort of self-evident, the simplicity here, and that is multiple tenants, the happy customers at the top, are all virtually using a much smaller set of hardware, a much smaller set of machines and database instances. In this case, one very large database instance. What's interesting about Salesforce is we actually run tens of thousands of tenants or customers on one Oracle instance. Oracle is our underlying database. We'll be talking about some Oracle features, and we're certainly very much in tune with using all the features there. But we also have a surprisingly small number of operators or database administrators who maintain this hardware stack and this software stack, and it's very homogeneous. All of our customers, all of our code is running the same version of the third-party vendors, but also more importantly, the same version of our software. So what's interesting about our world is that software developers of Force.com itself are generally only working on, say, two versions of Salesforce, the one that is out in production, and of course we need to fix that when issues come up, and then the next version. And what this means is that we spend a great deal more time doing innovative things as opposed to fixing and patching other things. It also means that all of our customers are on the exact same schema. And in fact, the schema itself is shared, and we're going to talk quite a bit more about that. But we are experts at squeezing many different tenants, thousands of different tenants, into a very small number of tables, and that will be the subject of other slides. So here's where the religion part comes in a little bit. And this is something that we have successfully avoided doing, which is the temptation of building a stack or maintaining a separate code line for a particular tenant or a particular customer. And there are lots of reasons one might want to do that. The customer may not like our upgrade schedule and may want to do it at a different time, or may want a particular feature, or may need to optimize. Those are all theoretical reasons. But we've found, and it's part of our religion, that we want to do our optimizations for all of our customers and use exactly the same functionality and exactly the same engines or kernels of code that are able to render applications sort of dynamically tailored to each customer, and that's where the metadata comes in. So our opinion is that probably no other vendor takes such a hard approach to this, but it's really one of the secrets of our success is that we have never done this picture. We have never built a separate stack for any one customer. So with those few introductory slides, let's talk about what that implies for the actual rendering of applications. And this is a little bit complicated. I'll go through the different pieces, and then in particular the box at the upper left, which is the database, is what we're going to talk about a lot here. So, the major areas of persistence for us are the data tables, which is your data in some sense, the customer's data, but also the metadata, of which we actually have a lot more metadata tables. All of our data that is configured by the setup screens or by our APIs are stored in Oracle, and that is our system of record. And where the magic happens is the code that we write, the Force.com kernel itself, is a series of engines or modules that interpret at runtime tenant-specific information, typically stored in metadata tables, along with the actual data that we read for a particular request. And what ends up popping out on the screen are polymorphic applications, meaning very specific screens or very specific workflows and very specific business objects for each of our tenants. But the same kernel of code, the same code base, is able to render these very varied applications. And those of you who are familiar with the variety of sizes of organizations and industries of organizations, all of that is rendered by the exact same code base, working off of a common set of tables. So before we go into the tables with a little more detail, it's important to just mention some of the principles that our development organization has used, which interestingly enough, in the 6+ years that I've been with the company and for the 10 years that we've been at this in general, most of these principles have stayed the same. And they are generally the good principles, we think, of building sort of a web application server and the platform. And those are, again, the database as a system of record and our application servers as being workers but not areas of persistence. The concept of no DDL at runtime. So this is another sort of surprising fact, which is although we have tens of thousands of tenants, we never build tables for any one tenant. We share tables. We are, again, masters of stacking different organization or different tenants' account data, for instance, into one unified account table. Now, how do we do that? We take a large advantage of partitioning, both at the physical layer as well as at the application server layer, which we'll talk about later. But for instance, all of our physical tables are Oracle hash partitioned on a very important column called org ID, which is essentially the tenant identifier. So this is the column that differentiates customer 1's data from customer 2, and it is in some sense the most important column of the table, and it is one of the basic parts of our query plans. Another basic thing that we'll talk about when we talk about our schema and our IDs is this notion of a smart primary key, and this is what allows us to play some interesting denormalization and polymorphic tricks, which is we will have special pivot tables that we'll talk about in a second that can be children of multiple different tables. In any given row, we know what it's a child of by looking at, for instance, the first 3 characters of the primary key, which is what we call the key prefix, and that identifies what type of ID it is. So we have the notion of GUIDs, which are globally unique IDs, but embedded in that GUID is the notion of object type, and we take advantage of that in many places. And because we are written for one particular database platform, we are able to take advantage of every performance trick, and we do shamelessly. So here's a simplified view of some of our most important tables. And this is sort of blowing up the database block that we had a few slides ago. I'll be talking about these in more detail, but generally speaking, we have a couple of key catalog or metadata tables, which are control information for the other tables. The rest are much, much larger tables, and in particular we have the raw data or grid table, which is where, for instance, all custom object data is stored. And then surrounding that as sort of a constellation is a series of specialty tables which make things work faster, so-called pivot tables. And I'll be describing ways in which these pivot tables are used for optimization purposes. So let's go into these three main tables. We have two catalog tables and the main data table. First, we have the objects table. By the way, these are not the exact physical names we use, but they're good for illustration purposes. So as you might guess, the objects metadata table has one row for each concept of an object or a table in your system. So if taking an example that I like to use, if you were to use Force.com to build a stamp collection application, which you could perfectly well do, then one row would get created here when you define the stamp object. You'd have a name, and it would have an object ID, which would be used elsewhere to associate to this object type. The fields metadata table, catalog table, as you might imagine, will have one entry for each field or attribute of stamp. For instance, country, price, etc. would each have a field. Now, this is very similar to most relational databases, which have the basic notion of types, text, number, string, Boolean, etc. We have all of those. But Salesforce and the platform, since one of the themes I'll be talking about here is that although underlying it we're providing a database, we're actually providing an application server and many, many other services in addition to data services. One example of that is that our field types are much richer than your typical database field types. We have pick lists, and we have foreign keys, and we have multi-select pick lists, and we have encrypted fields. We even have fields such as addresses, which are made up of multiple components and know how to render themselves as addresses. So this is an area that we've spent a lot of time because we know that rich field types are important to application designers. Now over on the left is a massive, massive table that we'll just call data, and this is in some sense a heap or a grid of all of the data in the system. We'll be showing some example rows in a second, but basically this is the real customer data which is controlled by the other table. So as stamps themselves were created, rows would be inserted in this table, and a primary key would be created. By the way, the first three characters of that primary key would tell you that it was a stamp. And then what's interesting is that the actual field data will be stored in these flex columns, val 0 through val 500. At the moment, we allow 500 columns, although you'll notice there's 501, those who are looking carefully, and that's for a certain maintenance operation that I won't go into. However, what's interesting is that various systems use flex fields. We use flex fields plus pivot tables to achieve our dynamic schema, and I'll be talking again about those pivot tables shortly. But briefly, when you were to declare your first attribute, such as country for stamp, the country values would be stored in val 0, the column val 0. What's interesting is that one organization's val 0 may be used to store text, whereas another organization, or even another object type within an organization or tenant, might use val 0 to store a number or a date or a different data type. And so that will bring up interesting questions. But we do store these in textual representation, which brings me to the next slide. Here's an example of some rows. We have primary key values, which you'll see are prefixed by the object ID, which is the type. All of these objects belong to one org or one tenant, but there are several different types of objects here. And you'll notice that the different types of object, although I'm not giving more detail about what these are, the first object has what appears to be text in the val 0 slot, and the second has a date in our canonical year, month, day format, which is an internal detail, and the third object type stores numbers. All of the conversion about treating these values as their correct semantic data type is done in Oracle using standard conversion utilities. And yes, there is a small penalty to this, but the benefit is great flexibility across our customer base and across their object types. And because of the other optimizations that we do and the hardware that we bring to bear, this is actually a fairly minimal performance cost of conversion. Of course, many of you are probably wondering, well, that's nice. You have a very deep table with maybe millions of rows and text representation, but what if I want to find, for instance, a stamp from a particular country? What if I want to run a selective query against this data table? Well, naturally, we cannot put Oracle indexes on the val0 column for several reasons. For one thing, a table with 500 indexes would have a lot of indexes and be very slow for data manipulation. But for another reason, this column has data of various different data types, so we wouldn't be able to index the rows as numbers or as dates. So we use a different technique, and this is where our first pivot table comes in. And I'll be introducing now the indexes pivot table, which is similarly large, in fact, much taller than the data table, but also much, much thinner. So by pivot table, we mean this is essentially a name-value pair table, a little bit more sophisticated. What happens is the administrator or the designer of this application indicates that a particular attribute needs to be selectively filterable. They may know that the country of a stamp, for instance, is something that people will want to search on with equality or other operators. So that will signal us to maintain the rows separately. In addition to storing the data in the val0 data table, we will denormalize the slot, that entire column for one particular object, into this indexes table as a name-value pair. And if we look more carefully, this table will store what tenant does it belong to, what object type is it, and then field num is the pivot. That is the number that corresponds to the slot for this row. The primary key is obviously the overall row that this belongs to. And then at the moment, we happen to have 3 columns to store strings, numbers, and dates, which are indexable types. We could just as easily have 3 indexes tables, but we happen to store them in this one table. What's interesting is that this table has a real B-tree index on each of the columns, string, num, and date, meaning that a selective Oracle SQL query can be run against that particular table, filtering appropriately to find the stamps that have a particular country. However, unlike sort of a basic index, which the Oracle optimizer knows to use, when you run a query against one table that has an index, the Oracle optimizer just knows to use that index. Well, notice here that in order to use this index, this multi-tenant index of Salesforce, we must inject a join to the indexes table. In fact, we must inject a leading join. We must lead with this table and then usually nested loop onto the data table. So what that implies is a sophisticated SQL generation, which is a very core competency of the Force.com platform. Naturally, all of the places that we query custom object data, that being reports, the API, related lists, and the UI, they all need to be aware of these pivot tables, this table in particular. And this area, query optimization, is something that I and others have spent a lot of time on. It is something we're very proud of. And so multi-tenant query optimization, several slides we'll be talking about in more detail, but the preview of that is that we build our own optimizer to augment the underlying relational database optimizer. So moving through some of these other pivot tables, as sort of an interesting side note, one of the features of the application is the notion of field uniqueness. Now, many people know that one of the better ways to implement field uniqueness is to use an index, a unique index. So the previous table indexes is actually used for non-unique indexes, which is useful for many purposes. There may be stamps from multiple countries and you want to find them. But sometimes there's a field that you really don't want any 2 rows of the same object type having the exact same value. Well, what do? We have a separate table, which I won't show you here the details, but it looks very similar to the last table, only the physical indexes built on this separate unique fields table are unique, meaning that when we maintain the denormalized values, when we write data, the Oracle index will throw up, will complain if a unique index violation would occur. Force.com then does the nice job of querying the duplicate data, and the end user error message ends up telling you the row that you have a duplicate with, which is a nice feature of our platform. But basically what's going on here is we're delegating to the underlying RDBMS the ability to give all of our customers in this virtual database multi-tenant way this important feature. And that general technique, while it's not the only technique we use, it happens to serve us very well. again, standing on the shoulders of the underlying relational database, providing higher level application functions. Yet another pivot table of interest is for foreign keys, which is actually very similar again to the indexes table. We just happen to break this out again into its own table because foreign keys are super important. Now what you'll notice, the reason we need this table again is while the raw foreign key IDs are stored in row in the main data table in the appropriate val slot. So if I'm a child table, then my parent foreign key would be stored in the val slot. But what if I need to find from a list of millions of children all of the children for one particular parent? Again, that's a selective query, so we need an index. And again, we use this special, very tall, very skinny, very important relationships pivot table, which is basically a forwards and backwards navigating table between parent and child. And again, all of the queries that we issue, whether they're related lists or mobile queries or reports, they need to know to inject this table in order to navigate relationships from parent to child efficiently. And that, again, is the job of our query optimizer. So that's finishing up the story on several of our important pivot tables. Before moving on to the higher level application functionality and the data update part of the system, just mentioning a couple of physical things that we do. Again, as a sort of low-level Oracle, I mentioned before that we partition tables, and this does a number of things for us. It means that our indexes are shallower and our maintenance operations are easier, and this is all internal details that just improves the performance of the overall platform. We also are big users of Oracle RAC, which is a clustering technology both for performance and reliability. And our application tier is very much in tune with the fact that we, for performance reasons, tend to locate a given tenant on a single RAC node. And if you're familiar with RAC, the purpose of that is to minimize interconnect traffic and to just have the cache on the particular physical host be more effective. And so our application tier, again, in sync with our data tier, knows to send queries for a particular org to the appropriate connection pool. The application tier itself, we've recently made it similarly have a notion of affinity. Although the application tier, any app server can service any request for any org, which is a very important architectural principle of ours. We have made it so for performance, when things are all up, we tend to send requests for a given organization to a small set of application servers so that metadata caching, which is not something I've talked a lot about, but which is very important for performance, it increases the effectiveness of that cache on our application servers. So here's just several examples of core low-level infrastructure that is really an expertise. Many of the things I'm mentioning here have taken us several iterations, but that is the beauty of our platform, and what I mentioned before about innovation that we're able to do is we are able to swap out subsystems than we do with regularity because A, we're not spending as much time patching or fixing really old versions of our service, and B, we are constantly monitoring and looking for areas for performance improvements. So with that little bit of digression, I'm going to move now on to higher level parts of our platform, of our Force.com framework for building applications. Here are several important areas that we'll be talking about. One of the interesting ones is the sort of blending of declarative features, by which we mean things that you describe the way you want them to work without necessarily having to write code. And this traditionally has been Force.com's bread and butter, which is letting business users describe sophisticated functionality, and then the kernel, the engines that we have written, knows how to render that properly, some of which is quite difficult to get right. In particular, the save engine is something that we're quite proud of and have spent a great deal of time on. Bulk save, by which we mean updating many rows efficiently and doing many things such as validation rules and sending emails and triggering workflow and running Apex triggers, importantly. This is very much a core competency of our platform, of our web service API, something we've spent a great deal of time on that everyone benefits from. There are other functional things listed here, such as our recycle bin and full text search, that are deeply integrated into Force.com that you get for free, that are quite difficult to write from scratch on a native database, that are just, again, higher level platform features that are part of Force.com that take advantage of the multi-tenant tables, the multi-tenant query optimizer, and all the things that we've been talking about so far. So let's jump into some of these. Let's start with some things that you're familiar with, such as our setup screens and the declarative parts of the application. So a real simple example is tracking field history. A pretty obvious thing, which is declaratively an administrator can say, I would like to know or track the delta every time the following fields on the following object are changed. This is a pretty basic thing, but a very important feature for auditing and other compliance reasons. And by the way, the storage of these name value, or excuse me, these changed values, which is visible in the app as a related list and queryable and reportable, this happens to be stored in another massive pivot table, by the way, as one might imagine, because of the dynamic nature of this feature, which is again done automatically by our save engine in response to this request, to this metadata request. The storage of it is all maintained efficiently for any column in any object. Moving up in sophistication, we have the concept of formula fields, sort of like Excel formulas. This is pretty easy for a business user to set up, and we then generate appropriate SQL to calculate this in reports. If they're inline formulas, we can do triggers based on these values, all in bulk. And so this is again an important part of our what we call schema layer, or our data modeling layer, that is very easy for our developers and business users to use. A little bit more sophisticated, actually quite a bit more sophisticated in the declarative world, is something we introduced more recently, a declarative roll-up summary field. This is, I would like to know for each parent how many children it has, or the max of its children, or the max of some expression of a child. A pretty common SQL aggregate function. However, in order to run a report on the parent and filter on the number of children, etc., we determined naturally that we needed to denormalize that value. We needed to calculate on the fly, or not on the fly, as the system is being updated. We maintain these summary values in an actual field slot on the parent, meaning that as data is inserted, updated, deleted for children, we are synchronously maintaining these parent values, which is a fairly involved operation that we've spent a lot of time optimizing. I'll talk about this a little more in a few slides, but hopefully you're getting the notion that some of these declarative features, in order to make them scale and be as flexible as we've made them, required quite a bit of innovative engineering on our part. So that brings us, I've been talking about this save engine, which is a real critical part of our core competency. And the key word here is bulk, and that is a proper web service API, we believe, needs to not be very chatty. So many of our customers, our API traffic is phenomenal. It's more than half of our overall requests. A very typical thing is to send us data to be inserted or updated or deleted, and oftentimes a great deal of data. So we need to be able to process hundreds, thousands, tens of thousands, millions of rows efficiently, while doing, as you see here, a very interesting pipeline of declarative and procedural rules. The declarative rules we've been talking about, those are things like roll-up summaries, and those are things like validation rules. Those are all fired and executed accurately as part of our bulk save engine. More recently, we've integrated, of course, Apex code, which allows you, the developer, to augment the save logic via triggers, which could call other Apex code, which could loop back and do yet more DML. So this is a pretty complicated area, obviously. But some key areas where this bulk save engine shines are, for instance, removing rows that have some error. Let's say you send 100 rows, 2 of them failing a validation rule or an Apex trigger. We will efficiently cull out those 2 rows and reprocess. After rolling back to a save point, we will reprocess the remaining 98, which is what we like to call a not all or nothing save, a sort of looser notion of save, because after all, when the web is involved, it's often the desired behavior to process as much as possible. Now, by the way, you don't have to do that. You can say all or nothing, but a typical web service request does process as many as possible, and that is a core competency of our save engine. Several other areas of sort of intricacy in our bulk save engine, best practices that make the system tick are listed here. We have the notion of avoiding deadlocks by automatically sorting the rows in primary key order. So if you give us 100 rows to update, they may or may not be in a consistent order to another thread that is updating the same 100 rows. So best practice is sort the rows in some deterministic way. We do it by primary key. And in fact, when there are multiple tables involved, we update tables in the same deterministic order. This is not easy to get right, but it's something that is very important for our system to have high throughput, so we spent a lot of time on it. I mentioned before the roll-up summary field. If you were to change the definition of a roll-up summary field, but you had many millions of children and parent objects, naturally the recalculation of that takes some time. So this is an area of queued up asynchronous processing, which we're doing more and more of to maintain real-time response time, but also accurately maintain your requests in the background. Other areas where we do that are field data type changes, for instance. So for instance, if you were to change a field from a text to a pick list, the storage that we use for that is actually internally different. So in the background, we would rewrite that field in such a way that it would behave as a pick list where it used to be a text, and we would, of course, preserve all your data. So these are just some examples of rich data processing that the Force.com platform does on top of our multi-tenant table, on top of our performance and query optimization. I'll quickly go through these couple of other functional areas. Those of you who are familiar with the system know about our recycle bin metaphor, which allows business users to cascade delete a rich data object. But by rich, I mean, for instance, an account and all of its children data, all of its contacts, all of its related custom objects are sent to a place where it can be recovered. Now, the tricky business here is we actually allow recovery after other commits have happened, after even schema modifications have been made. So if a business user were to delete account number 1, and then the administrator were to delete a field, we would still allow account number 1 and all of its child data to come back within a week or so. There's a time limit on this, but I believe it's about a month. And so that functionality of recovering deep business objects across schema changes is not something that is typically provided by relational databases, but it's something that we provide with Force.com. And one other very important functional area is integrated full text search, something that our users take for granted. They can run reports and do SQL filtering, but oftentimes people just want to look for words in all of their data. So this is an area that we could spend an hour talking about alone. It is an asynchronous system that maintains in the file system a full text search engine, so a separate data store that is automatically updated as records in the main system of record. The main database are updated. The full text indexes are also maintained and then made available within seconds or near real time to the UI for the search box or to Social. Social is our query language for search. So this is just another core competency, something very difficult to get right in a multi-tenant environment that we provide for free as part of Force.com. So I've been hinting at optimization. I think we'll talk a little bit more about that now, which is our kernel that takes all of this metadata, the definition of objects, the definition of fields, the definition of what the user wants to do, and consistently outputs the appropriate SQL, because after all of our data is eventually retrieved via SQL to efficiently get the appropriate data. So like all good optimizers, it is aware of statistics, or all good modern ones, I should say. So there is a fairly elaborate set of statistics that we gather. Some are gathered synchronously, some are gathered asynchronously on a weekly or daily basis, and all of these inputs go into the eventual query generation. One area that I will mention is that data sharing being the ability to say these users have access to this row, to these rows. That is another SQL-intense area of our system. We actually store that, as you would imagine, in a series of tables. And it's a rich model. It's hierarchical. So integrating that semantic feature of data sharing into our query engine is another very important piece of the query optimizer, because oftentimes the evaluation of what rows you can see is one of the more expensive parts of the query. And we'll see some examples about different ways of doing that in a moment. So here's kind of a view of the pipeline that happens during query optimization. The user submits some query in various forms, reports, API, UI. We then look contextually at what do we know. We know the filters the user has applied. We also know things such as who is this user and what do we know about him or her in terms of visibility to this entity. Based on all that information, including what custom indexes are there, indexes being the value stored in that indexes pivot table I described earlier, and what statistics do we know about those indexes. From all of this information, we then choose the appropriate query to write. And what's interesting here is that, again, the query that we write is sometimes a hint. Sometimes we use Oracle hints to direct Oracle what to do because our application, our query optimizer, has available to it this additional information about our application and user statistics, etc., that the underlying relational database cost-based optimizer cannot have. It only sees the raw data. We have more information. We know how many rows total are in this particular tenant account table, for instance, whereas Oracle only knows the total size of the account table. But a point I want to make is that sometimes the SQL that gets emitted is not just changed by its hint, but is also changed by extra joins. These pivot tables must be joined in. They must be led with. We must tell Oracle, lead with the indexes table, lead with the relationships table because of our analysis. So here's an example of the type of analysis that we might do, different choices. If, for instance, a high selective filter, a very specific filter is applied, and we know that, for instance, pick list fields, we keep histograms of each pick list field, and we know values that are low cardinality. So if the user were to do an equality filter on a low cardinality pick list, then we would hint the query to start with the indexes table and then join to the main table. Alternately, if there were no selective filter, but we did know that the user happens not to see a lot of rows, only has visibility to a small number of rows, then that means that's the most selective part of the query, and we would hint our query to lead with the sharing tables. And a final example is if there's no good filter and the user sees most or all of the data, then we go with typically a hashing plan, which basically says read all the data off the disk and hash it all in memory efficiently, which is the appropriate Oracle plan for a large report, for instance. So a lot of sophistication goes into these decisions. But importantly, because of the refactoring that we've done, because of the code consolidation that we've done, the same decisions are made throughout the application, leading to the performance that we see. Okay, so we have a few minutes here before I take questions, and it's going to bring me to the procedural part of our platform. We've mostly been talking about declarative things that the Force.com does for free. Of course, most of you are aware that a few years ago we introduced Apex, which was a big deal for us. That was the notion of us running code written not by us, code written by our customers, by our partners. So there are some constraints that we went with Apex, such as governor limits that I'll talk to in a moment, but Apex itself is actually just another module, another kernel that makes up the Force.com platform. We interpret it, we parse it, we interpret it. We actually store it in something similar to a bytecode format at runtime so that multiple threads can execute the same Apex class. We've gotten quite sophisticated at that. But at the end of the day, mostly what Apex does is it automates the other parts of our service, such as the query engine, such as the save loop. Because what Apex essentially lets you do is procedurally wrap a large transaction, multiple queries, multiple update statements, and the whole thing must succeed or fail, controlled by your business logic. So I mentioned this here, but Apex itself, when you compile Apex or save Apex, it goes into our database, it goes into our metadata tables, and then at runtime, the definition of the code is interpreted, put into a format that is runnable, and then the Apex runtime or the Apex virtual machine, if you want to call it that, is then responsible for executing those instructions as appropriate based on the triggers that are defined or the web service calls that are defined, etc. But at the end of the day, Apex, again, simply calls the same query optimizing code to read data and the same save logic to write data, as our public web service API or our UI or any other data manipulation in our system. And that is a very important concept. So again, because we have control over Apex, we've built into it many useful idioms and many useful features for integrating with the rest of our platform. They're very good. The syntax for doing bulk save, all or nothing, is very easy in Apex. The ability to queue up messages or queue up a new feature is the ability to queue up asynchronous work, which will then reliably be processed. This is all idiomatic and very easy to do in Apex. Ability to process XML, expose your Apex methods as web services. We've tried to make this as trivial as possible because we know these are the core things that people in modern web service, platform as a service environments want to do. And so that's where we've been putting a lot of time. But again, the theme here is that Apex is just one component of the Force.com kernel sitting on top of metadata, sitting on top of a multi-tenant database that then renders your dynamic application. And I mentioned the governor limits, but this is the general notion of protect the service. So naturally, since we have shared resources, we have many shared resources, and we in fact run, a surprisingly small amount of hardware runs the world, the Salesforce world. So we are very careful to control or govern mostly not malicious usage, but mostly runaway usage or accidental abuse, we might say. So Apex is certainly a big believer in this, and this means a given Apex request can only consume a certain amount of cycles and a certain amount of heap storage and do a certain number of database calls. And while we realize for certain applications this is difficult, we also have seen, we understand in our teaching and have seen that it leads to better code. For instance, our encouragement or requirement that Apex be written in a bulk manner means that the throughput of the system for everyone is much faster. It is much easier to process 100 rows in Apex all at once than to do 100 rows inside of a for loop 100 times. And that is one of the purposes of these governor limits. Another area that Apex has sort of broken ground as far as not just being a programming language, but being an environment or a development environment, and part of a deployment mechanism is this notion of unit tests, forced unit tests. So again, our customers, our partners are not able to put Apex code into production unless code coverage reaches a certain level, which is an integrated feature of the platform, one that's very useful. You as a developer, after writing these tests, can press a button and see that a change you made did not alter the behavior of your system. You can see which lines you haven't covered and what tests you need to write. But an immersion property of this, which is very important for us and therefore very important for the Force.com community, is that by asking our customers and our partners to write these tests, it builds up a canon, an ever-increasing canon of tests that we, Salesforce, when we do an upgrade to the service, we are able to regression test very sophisticated functionality by asserting that all of your tests still pass. So we do this, by the way. Before we do a major release, we assert that all Apex tests still run. It's a very important part of our deployment universe. And the end game, here's a graph that's a little bit old that shows, considerable increase in traffic, the red line, while steady or in fact decreasing time to response. So the net of all the work that we do, and in fact, we put our most senior folks on this area, which is performance, performance, performance. All of the things we've talked about have led to a highly functional, highly used, increasingly used, and yet highly performant system. So the final slide and the takeaways from this is platform as a service, which is frankly quite, our approach, we believe, is quite different than a number of the other sort of more infrastructure-focused platforms. We don't give you as raw access to hardware, and in some cases we don't give you raw access to coding as some alternative platforms, but the trade-off for that is we give you much higher levels of abstraction for very common database and application features. And that is the notion of Force.com's mature platform as a service offering. Again, all of which is optimized for all the things that you see here. So with that, I think we will take some questions, or I have some questions here which I will answer. So the first question I'm going to look at says, with tables partitioned by org ID, are not some partitions larger than others, different customer data sizes, causing imbalance and subsequent performance impact? A good question. So remember, Salesforce has many thousands of customers, and absent the skew of several very, very large orgs, the algorithm that we use tends to splay the organizations across our partitions in a fairly random way so that at the end of the day, the partitions tend to be relatively balanced. Now, it is true that some, particularly some that contain very large organizations, are larger than others, and that does affect some of the timing of the maintenance that we do. But in terms of query performance, any one of those organizations, we might choose to have a slightly different query plan, such as more full scans of that partition for that particular organization. But overall, the system is fairly balanced. So the next question that I'll answer is, what steps do you take to ensure that data from one org cannot be accessed by another org? Obviously, a super important question. So this gets at the very heart of the notion of a virtual private data or virtual database that we give each of our customers. And the reality is we do this by filtering every table by org ID. So one thing I didn't mention is these tables are partitioned by organization ID, and all of the physical indexes on these tables lead by org ID. Meaning, hypothetically, if there were a query in our system that were not filtered, it would do a full table scan across all partitions and probably never finish, particularly if it were a join. So that is sort of job one, is that our query optimizer and the other SQL that we emit is always including an organization ID filter, and if it didn't, it wouldn't return. But that's not the whole answer. We have a lot of static code analysis to ensure this. We also system test very thoroughly each release, and we would see queries that weren't organization ID filtered, which is just not something that happens. What is the total number of tables and indexes in your multi-tenant schema? That's probably an interesting bit of trivia. Surprisingly small. There are more metadata tables than actual tables that hold the data, the big data. Metadata tables is on the order of a few hundred. Let's call it 200 or 300. And then the data tables and the pivot tables that surround that is probably on the order of about 100 tables. So what's interesting, again, is that we have 50,000 plus businesses with varying different industries and uses of our system, all sharing what is essentially 400 tables. Maybe it's 500. One thing I should mention is that we have, you can see this on the trust page, we have about 10 pods at the moment. A pod for us is the self-contained unit of Salesforce. It includes the databases and the application servers and the search servers. It is a standalone ability to run our service. And although we could run the entire world on one pod, for sort of safety's sake and for geography's sake, we have a smallish number of them, much, much smaller than our number of customers. Let's see. How do you back your report queries? Do you use a BI platform? Are you replicating ETLing to a different DB for report queries? A very timely question. So this is about the analytics part of our system. So as of today, for better or worse, actually kind of an interesting story, all of our analysis is run off of the same OLTP tables that the OLTP part of the system is running on. So we have done a number of things to optimize that, denormalization, et cetera. However, we are currently, and so the short answer is we have written, our BI platform is our query optimizer, and it is currently running on the same tables as the OLTP part of the system. Now, we are actively at the moment looking at building some special purpose tables and possibly, heaven forbid I say, building tenant-specific tables for our largest orgs to facilitate BI and more star schema and analytic queries. We are definitely looking at building additional special purpose structures, which we will do sort of more sophisticated full scans and more sophisticated hash joins and probably more sophisticated Oracle parallel queries. But the short answer is we don't at the moment ETL. Now, one good aspect of that is that all of our reporting is by definition real time because it's literally run on the same tables that are transacted against. If you were to design this all over again, knowing what you have learned since the start, would you use a non-relational data store for some parts? Well, I'll admit that I'm a bit of a relational bigot myself. However, we are looking at, and a good example of this is something that we call FileForce, which is we traditionally have stored all of our blobby items, such as attachments, documents, etc., in the database because we used the same backup strategy and there was a certain elegance to storing everything in the database. Of course, given the disk cost and the sophistication of the transactional part of the system, that is a bit overkill for a number of these sort of less frequently accessed larger objects. And so we have recently, a great example of a refactor that we have done, we have recently are in the process of taking out a lot of these files or general blobs and putting them into a reliable sort of similar to a Google file system with redundant copies on much cheaper hardware using more commodity hardware. So that's one area where we are actively doing this. Now, there are several other areas such as session key management and several other things where we are actively looking at other stores. But I think my general answer to the metadata, the core metadata, and the core business data is no, I think we would stick with a relational store because we get an awful lot. You know, our system, unlike many other PaaS systems, has very high semantics as far as the ACID semantics of the database, the reliability of our backups, etc. And so we do get a great deal of that from our underlying RDBMS. Let's see. Based on your slide demonstrating the data object, does that mean that if when separating an existing instance into two, are A, record IDs maintained in a switchover, and B, are record type IDs maintained in a switched over to new? So we have occasionally done splits, meaning we take an instance and put it onto two different pods. And in that case, we do preserve IDs. Will you ever be able to support composite indexes or external IDs? So that falls into the yes, we certainly could. It's a functional improvement we could make. We've talked about it, and we could additively do that without substantively changing our general scheme. Is Apex run using the JRE? Good question. So I hinted at this before, but Apex, we've basically written our own virtual machine. But Apex itself are really POJOs, which stand for plain old Java objects. So we interpret using Antler, as a matter of fact, our own grammar for Apex. We parse it, and we put it into what we consider a compiled form, but that compiled form is actually just a Java object, which we then, quote, execute. Executing it just means running it, or interpreting it, if you will. And so it's not really, we are certainly not generating Java classes. We don't generate Java bytecode, which several people have asked. Instead, you can think of Apex more as an interpreter, but where we actually parse it into a format that is more efficient for multi-threaded requests. Is Salesforce's sharing model integrated with the pre-query optimizer? Absolutely. Although you do mention the word pre-query in that question. So I didn't mention that before, but when the optimizer is doing its work and deciding what to emit, we don't always have the answer. We don't always have enough pre-calculated statistics. And so one thing that we do is, in order to avoid a really bad query plan, we will pre-query. We will run quick queries to test the filters that the user has provided to see if they can be satisfied quickly. And if so, we will use that information when we generate the large report. So for instance, if we know this report is going to take a long time, we will, in fact, use both the sharing information as well as these pre-queries in deciding. And so this is something that's called dynamic sampling in other database systems. So we do that automatically. I think I'll take one more question here. When will you support more than one level of master detail? Very important question, and the answer is it's currently checked in, and I believe the release plan is for spring of this year, or our next release, essentially. So many people have asked for that, which is a very important new declarative feature of our system, and you'll all be happy to hear that multi-level master detail is on its way. So finally, I'll say, where do I go for more resources? So the screencast and the FAQ for the webinar will be available early next week at developer.force.com. Also, people will get a follow-up email. Finally, there is a white paper. I should have mentioned that earlier. The contents of this talk are actually based on a white paper that we put together called the multi-tenant white paper that is on developer.force.com as well. And I encourage you to download it and read it, and it will provide more detail than we had today. So thank you very much for your time, and hopefully this was useful.